I'll try to make them short and sweet. The first one we're going to talk about is Newton's method. This is, again, kind of part of that whole thing where we're just kind of covering a few little odds and ends before we move into antiderivatives and integrals. So Newton's method is a way for a technique for us to be able to approximate the zeros of a function, okay? And what you do is it kind of piggybacks on that whole intermediate value theorem. Remember, the intermediate value theorem said that if you're on this closed interval and you have values that change, right? The value of the function changes from positive to negative or negative to positive on that closed interval, and somewhere in between there has to be a zero, right? We talked about that. And this is similar to that in that, okay, well, if I'm talking about that closed interval on A to B, and I've got a function that's differentiable on that interval, okay, then there's got to be a zero in there. And is there a way for us to approximate what that zero is? So what we do is, if you'll notice in this first picture over here on the left, what we do is we start with some initial guess. Okay, generally you're going to guess using your calculator and pretend that you can't just click on the answer. All right, maybe it's a little bit more involved than that, but you want to have a guess. And if I pick some value at x naught, that's my initial guess, then the derivative to the function at that point, right? The derivative to the function at that point is going to cross the x-axis at x1. Everybody see that? Okay, so that's kind of an approximation then that we're going to look at. Now, as I continue this repetitive process, this time if I take x1, so I'm on the second screen that you see here, if I take x1 and I find the derivative at that point and the line, the equation for the line that passes through that point, you'll notice now I have another value x2. That would be an approximation as well, okay? What do you start to see that's happening? If we cross the x-axis at r in this image, each time I use that approximation, my x value, so I started at x naught, then I had x1, then I had x2, now I have x3. What are we doing? We're getting closer and closer to the actual value where it crosses the x-axis, okay? So Newton's method is really just a way for us to be able to approximate what the zero is of the function using derivatives, okay? So we're just going to practice a couple of those methods here. And we're going to see how it actually works. All right. So when we look at this, Newton's method is based on this formula down below. And I'm going to show you the formula in just a second, but I want you to kind of see how that formula comes about. So we know that the equation for our line that is crossing, let's say we want to know what is the equation of this line here at our initial guess. So we have our initial point, we have the slope of that line, which we're coming up with using the derivative, and it's passing through a particular point. So the equation for that tangent line is found by taking y equal to the value of the function at that point plus the derivative of the function at that initial point times x minus the initial point. Okay, that's just the point slope formula. We've done that plenty of times before. We're talking about it going through a particular spot. Now, if we want to get particular and say, okay, well, what happens if we are talking specifically now about passing through the point x1, 0? In other words, what's the approximation of x1 using that tangent slope we were just referring to, right? Okay, so that kind of changes our formula just a little bit here if I plug in a particular point. So I'm going to say 0 now for the y value, but it's still going to be based on, this initial one is still based on the value of the function at x naught plus the derivative of the function at x naught times x1 minus x naught. There's a lot of x's in that particular case, but we're being very specific about the points we're looking at. And again, if I'm trying to use this initial equation to find out what's the value at x1, okay, then I'm going to simplify this. So I would end up with 0 is equal to f x naught plus f prime x naught. Well, I didn't really do anything there, did I? Okay, well, let's take this back for just 1 second because I don't want to distribute that actually. Let's do instead, I'm going to go ahead and I'm going to subtract f x naught to the left is equal to f prime x naught times the x1 minus x naught. Now I'm going to divide both sides by the derivative. That leaves me with negative f x naught over f prime. X naught is equal to x1 minus x naught. And if I'm solving for x1, I get x1 is equal to a positive x naught minus f x naught over f prime x naught. I rearranged a few things in there. But that gives me this x1. That's what I wanted to approximate. What is the value as that line crosses, using that line, the secant or the tangent line, excuse me. What is the value when I cross the x-axis? So I get an approximation, and we know that we can keep doing this over and over again. In fact, if I go back in and now I use, I'm not going to do it first because I don't want to. But if I used this same form of a function up here, and instead of us using the initial guess of x naught, now we come in and say, okay, I'm going to use x1. So everywhere there's an x naught, I replace it with an x1. And I solve this time for not this x1, but I would go in and I would solve for an x2, right? Because I'm going to keep getting these guesses. So I'm looking for a second approximation at that point. And nothing changes in this formula. It's a repetitive process, so we don't really need to see it go again, I don't think. But what we find out then is that Newton's method is about taking some first guess. Usually you use a graph to kind of help you out there. And then, just like we solved before, just like I solved above, you have this general idea that the x sub n plus 1, that's your n plus 1 guess, that's your approximation, is found by taking the initial x sub n minus the value of the function at that x divided by the derivative of the function at that x. So you just repeat it. Okay, so let's kind of go through this. Y'all take your graphing calculators. Let's see what this function looks like. Let's do this function right here. We want to use Newton's method to approximate the zeros for the function e to the x plus x. So e to the x plus x. It looks something like that, right? Sort of a line or a curve, I should say. All right. And if I couldn't click on the point in Desmos, if I wanted to know what that value was, how do you do this in your graphing calculator, by the way? How would I know what that solution was or what that x-intercept was using your graphing calculator? Somebody explain it to me. How do you do it in your graphing calculators? Not trace, the other method that you know. Second calc, what do you do? Second calc.
You choose side.
Try this. What if it wasn't? What if it wasn't there? Can you do second calc 5?
Yeah.
Oh, but you have to have this intersection, don't you? You have to have an intersection of two lines. Let's pretend that we did, right? We would have a line right here, and we'd ask our calculator to find the intersection of those two lines, right? That's what the calculator does. Do y'all know that? And you have to put in the left boundary, right? You have to put in a right boundary. And it asks you for a guess, which I never know why they do that, because you're asking it to tell you the information, and then it gives you the point, right? Yeah, that's how our calculators do it. That's how most computer programs do it. That's what it's using Newton's method. So we're going to be a bunch of calculators right now. We're going to be the computer. Using Newton's method, we're going to figure out what this point is right here, the same way that your calculator figures out what that point is. All right, that's what Newton's method is. Okay. So what we have to do here is we have our function. E to the x plus x. What is the derivative of our function? What's the derivative of e to the x?
E to the x.
What's the derivative of x? All right, so we have the function and we have our derivative. Okay, now if I go back and I look at my graph here, all right, I'm gonna just guess that this is 0.6. Are we all right with guessing that that's 0.6? Again, I'm gonna pretend that I can't click on it in Desmos, that I'm just looking at it on your graphing calculator. So 0.6 becomes my initial guess. X sub 0 is gonna be 0.6. Now, if we follow the pattern that we showed above, x sub 1 is equal to x naught minus f of x naught over the derivative of f of x naught. And I'm going to get some value. Okay? So let's look and see what that looks like. I'm going to come over here to Desmos. So all I did was rewrote Newton's method using our initial guess, right? Okay. So I actually programmed this in Desmos. You could program it in Excel if you wanted. That would be pretty easy, but it's pretty easy to do it in Desmos as well. We said the derivative of f was e to the x plus 1, right? Got my signs right? Okay. And we know that we're going to let x naught be equal to 0.6. And it's obvious that that's a calculator problem, correct? If that value would have to be a calculator problem. So you would put that into your calculator. This is what we wrote on our paper, right? X naught minus f of x naught over the derivative at x naught. And we can see that we have a value here of 0.2582, right? Yes? Okay. Now, that gets me an approximation. But the thing that you're wanting to do here is you want to keep repeating the process. So I have some number, I don't know what it was. It was like negative 0.2 something or other, wasn't it? Something really large. Okay. So I'm going to say, okay, now I'm going to repeat this process. I'm going to say x sub 2 is going to be equal to x sub 1 minus derivative at 1, or function at x1, derivative at x1. And I keep repeating this process until I get to some specified decimal value, until your iterations start to be exact, almost the same, to where they're only differing by a certain value. All right, so I'm going to come back over here to my screen that I have here. And we have almost, so you can see that I've repeated this process, and I can go one more time, many times as I really want. See if we change that to 4.
So we take the previous number, how many decimals in the round?
They're going to, don't round it at all. Okay, don't round it at all yet, which is why it's much easier to start seeing if you had, leave your screen. In fact, you all can, I think you can leave your screens onto your graphing calculators, right? You know, where you're seeing the whole thing. Don't round it. So in one section, they might say to go out 2, 4, 6. So as long as I go out, as soon as I get to 6 decimal places and those values are the same, and they are here between this guess and this guess, right? If I go out 6 decimal places, then the value of the approximation for x4 and the value and this one at x5 are the same at that point to 6 decimal places, then you can stop. There's another one I read, go out 9 decimal places. So you would want to look and see what your particular problem was, how far your problem was asking you to go out. It's just it's just a repetitive process, right? It's iterations, isn't it? To where you're just repeatedly doing the same thing, approximating it until you get closer and closer and closer. And it goes generally quickly. We only had to go out 5 places on this one. You can go out, sometimes it happens much quicker than that, which is why your calculators and the computers tend to use Newton's method, because it'll get there in a quick manner. Okay, let's look at another one. Let's look at, so in other words, we would say that the that value, and let's see how close we actually got. So see, it was the same number, right? 0.567 started to repeat. That was our value. That was our approximations that we got on 4 and 5, wasn't it? When I was down there. Okay. Let's try this one here. This one says, I want to know what is the x coordinate of the point where the curve crosses the horizontal line y is equal to 1. This would be another example of when you would do that second calc 5 inner, right? Where you're trying to find the intersection between 2 points. That's what they're doing here. Okay. So for here, we have our function, which is equal to x cubed minus x, or our equation, I should say, which is equal to x cubed minus x, and we're interested in where it intersects when y is equal to 1. So to use Newton's method, we need to set these 2 equations equal to each other. All right, so the function becomes x cubed minus x, which was equal to 1, or x cubed minus x minus 1, which is now equal to 0. That becomes the function that we want to look at. And the derivative of that function would be what?
All right.
3x squared minus 1. So we have the function and we have the derivative. Let's go graph the function, x cubed minus x. And let's say that we want to look at the interval. Let me see what this other one looks like also. Turn that one off. So it looks to me as if we have some intersection occurring between the interval from 1 to 2, right? It's occurring right here. Here's 1 right here, right? So we have some intersection that's occurring right there. All right. So if we wanted to look at the interval between 1 and 2, another thing that you can do is you can just split your interval in half. Okay. So if we wanted to say, we're looking at the interval between 1 and 2, let's take an initial guess. Let's let x not be equal to 1.5. So the first approximation comes when we let x naught minus f of x naught over f prime of x naught. And then we start repeating that process. So how many iterations do you have to go till you have 6 decimal places equal? See if you can find that solution. Do you have an approximation? Does anybody have a different approximation? Well, now you need to do it again, right? You gotta keep using,
Oh,
keep using
keep
that
going.
number. That what you got, Sydney? I want to know what the answer is to. So here, you have to keep using your current values. So this becomes your approximation, and then that becomes what you use. So you replace it in your calculator. 3.42, no. 1.324718.
So,
7. Okay. So that's what you should get, 1.32471. Can't remember where I had that number from. That's what you want to keep using. So you're going to keep repeating that value, right? You have to keep putting that value in and evaluate the function every time you get an approximation. So whatever this value here is now what you use for the derivative and the function. That becomes your second approximation. And you plug that back in. Okay, and keep plugging it back into your calculators. All right. Okay. Again, this is, and how many iterations did it take? 4, 3? 4, yeah. 4 iterations for it to come out to give you an answer. So it's generally a fairly quick process, which is why your computers and why your calculators do it. It does fail, however. Let's look at this one right here. It says the function f of x is equal to x to the 1/3. It's not differentiable at 0. We want to be able to show that Newton's method fails to converge using an initial guess of 0.1. So let's just use our calculator here. We know that the function is equal to x to the 1/3. The derivative would be what? What's the derivative? One-third x to the what? Negative 2/3. Okay. And so if we have our first value here and we let x not be equal to negative 0.2, excuse me, 0.01. What do we get when we put that in for this first iteration? X naught minus f of x naught over f prime x naught. What do you get? What do you get?
I got -6.
Negative 0.2?
No.
That's what you want, negative 0.2, okay? So we get negative 0.2. So now let's use negative 0.2. And what do you get? You get an answer. 0.4, is that what you said? Yeah, 0.4. Okay, how about for the third iteration? 0.4 minus f of 0.4 over the derivative at 0.4. Negative 0.8. Last one, what happens at x4 on our fourth one? Y'all know how to program this kind of thing in an Excel spreadsheet? It'd be pretty easy to put it in an Excel spreadsheet and make like a table, wouldn't it?
1.6.
1.6, 1.6. Okay, so we can stop here because the point of this is supposed to be, right, that we are getting converging on a particular value, right? That was kind of the idea behind the others, right? Our numbers kept getting closer and closer and closer to an intersection, right, or a solution to a particular problem. And right now, we're actually bouncing back and forth and getting wider and wider away from x is equal to 0, correct? This is an example of when you're not converging. That's the point of Newton's method, is that you need to converge on a particular number, as in taking the limit almost of a particular number. And so you just have to be careful to know that there are times when it doesn't converge. So it should have happened rather quickly, right? You should have started to see a pattern in which it was starting to converge on a particular number, and it's obviously not. All right. So you just want to be careful. If the method does converge, it should converge to a root. If it does not, however, it may not converge on the root that you had in mind also. So not only could it fail, if you pick a value, if you pick a starting point that's too far away, then it may give you a root that's not where you want. So not only can it fail, but you have to pay attention to what you're trying to converge on. This right here reminds me of when you are asked to find the left and the right boundary in our graphing calculators, right? When we have a curve like that, so that we can tell the calculator on what interval we want it to look, because it's looking for doing Newton's method on a particular interval. So if I were to start out here, and for whatever reason, I see, because I was pointing over here, look how it gave me the wrong area over there. So you just have to be careful with it. All right. Okay, that's Newton's method. There's, I don't know, 5 problems, 6 problems.
6.
Yep, over homework, for homework on that. Now, we move on into antiderivatives today. When we come back from Thanksgiving, we talk about definite integrals. In order to talk about antiderivatives and integrals, you have to know how to find the derivative. It's the same thing of knowing how to factor. You can't factor unless you know your multiplication facts. This is the same concept as this right here. Okay? All right, what I want to do is I want to take just some groups of like 3 and 4. Okay, so I'm going to get all of y'all to just group together and be fastest. All right, I'm going to get you 3 to group together and then you 5 group together. Right, that's the easiest thing. All right, quickly, what I want you to know, what I want to know is here I have the derivatives a through f. Okay, I have the derivatives a through f. And what I want you to do as a group, as quickly as you can, is I want you to take that derivative and tell me what the original function was. And I would like for you to go ahead and write the process here in the center. So start talking. You've got like 3 minutes to get this done. There's 3, 4, 5, 6 problems right there. Okay, and I want you to come up with a pattern or a strategy that you see in how you're going from the derivative back to the original function. Mark it, set, go. Putting a timer on this. Do we want to get out of here soon? Let's go quickly. We got 5 minutes. Maybe not on the first one. See if you can go through the next one. See if you can just like numerically show it.
Yeah.
If you think you've got it, take the derivative of what you think the original is until you get back what you were asking.
No, maybe should say.
Yeah, that's what I'm saying.
Gotcha.
Yes. One third X. Could you do 1/2? 2x, 1 2x, 5. Third.
Which way? Yeah. So since the same brings up this. I think since it's minus 1 greater,
So they
wouldn't just be 1 over x.
so
Because
how would you
take the derivative of 1 over x.
just negative 1.
You can make this x or negative 1. And then it's bring it from the part, which negative because if it's negative 1 x, right? Well, but if the exponent be positive, because whenever you bring it down, it's canceled. Minus
What times?
Alright, but you get a radius.
Always.
The next one's not.
I'm going for that.
The thing is, for this one, so we just write it.
So remember, once you get your original function column done, could you take the derivative and get what you were asking in the first column?
No, it's just.
I'm trying to figure out how to write it, and then if you take.
One over is, I just assumed you did this process.
Can you check ours?
No, we'll
Oh,
look at it in a minute. See if you can come up with a strategy if you've determined it.
Oh.
Wait, so would you write it as 1, 2, 2, that's.
Negative.
All right, are we done enough? Yeah? Communication. All right. So you should have something that looks like this. For 2x, if the derivative is 2x, the original function was x squared, right? Okay. If the original function is x, then, excuse me, if the derivative is x, then the original function had to be 1/2 x squared. Because what do? We add 1 and then stick it over that exponential sum, right? It's the reverse of the power rule. When we did the derivative, we subtracted 1, didn't we? Yep, we brought that exponent down and then we subtracted 1, okay? So what we are doing here is we are adding 1 and we have to put the that component back up there, right? Because if I were doing the power rule, I would bring the 3 down. The 3 has to cancel with the 1/3, doesn't it? To give me back the x squared, just a coefficient of 1 in the front, right? So what we're doing today, what we're talking about today, these are called antiderivatives, all right? So we're undoing, we are reversing the property of our derivatives. You can move back if you want, guys. Don't go back to your seats if you want. So we have to be familiar with our derivatives enough to be able to undo them, hence the reason why I'm suggesting that you keep memorizing and practicing with your derivative functions. An antiderivative is defined as the function f, capital F. It's an antiderivative of little f on the interval of I, as long as the derivative of capital F is equal to f of x. Don't get bogged down too much with the definition there. Understand an antiderivative is the reversing of the derivative, all right? An antiderivative is the reversing of a derivative. So if we look at this example here, I want to find the antiderivative given the function -2 over y cubed. So I'm going to rewrite this to begin with as -2y to the -3. The antiderivative, which we are defining as capital F of x, would be equal to then the -2y to the -3 plus 1, because we're going to add back that value to that exponent and put it over the -3 plus 1. So I have -2y to the -2 over -2. Those cancel, leaving me with just y to the -2 or 1 over y squared. That's the antiderivative. Okay, let's try that again. I want to know what the antiderivative is of the function -4 cosine x minus x. So capital F of x would be equal to the same -4 in the front. What is the reversing of cosine? Would be sine x, right? Minus, what is the antiderivative of x? That would be 1/2 x squared. Take that exponent, add 1. So 1 plus 1 is 2, and then put the term over the 2. Okay? And that's it. That's what we call the antiderivative. Okay? Now this process of taking the antiderivative gives us multiple solutions. So I want to just write something out here really fast for us. If I have, let's say f1 of x is equal to x cubed, and I had, and this is what we are defining as the function. What if I had f2 of x, which was equal to x cubed minus 5, and I had another one equal to x cubed plus 3. What's the derivative of the first function I have up there? What's the derivative of that? 3x squared. What's the derivative of the second one? What's the derivative of the third one? All right. So if the goal of this section is to take a derivative and go backwards and find out its original function, I have 3 different functions here that all give me the exact same derivative, don't I? All right, what is the only thing that's separating them? The constant. So when we take an indefinite integral, right, when we take and find the antiderivative, we take the antiderivative in the same way that we were doing it above, but we're going to tack on a constant, a c, because that's how these families of antiderivatives all differ. They're all just differing by this constant, because when I take the derivative, the constant goes away, don't I? So if I'm undoing that, if I'm reversing it, then I have to add back in the possibility of this constant. So we're going to add that c back in. So what we find here then is this operation of finding all of the solutions is what we call anti-differentiation, or in other words, which is a big mouthful, indefinite integration. Right? I don't have a boundary set on this. I don't have an upper or lower bounds. I have an indefinite integration, and it is the idea of finding that whole family of functions. And the way that we look at it is this. We have, this is called the, this is our integration symbol right here. We are taking the integral of f of x with respect to dx. It's important that you add the dx in there, all right? Just like we had before when we were taking the derivative. Once I perform that operation, the capital F of x is what we define as the antiderivative, plus the constant of integration c. Blaine, my son, the one that's home right now for Thanksgiving, was saying in engineering, he was like, yeah, they don't even do that anymore. They like drop it. I said, well, maybe it's like a tolerance then. They don't seem to be interested in that C. They do this all the time, but they seem to be dropping that off of there, which I thought was funny because he didn't really like that. All right, now, it's important that we understand what variable we're taking this with respect to. So the differential dx, that would be what we call the differential. It has to serve as kind of like a stopping point also for us to know where we're taking the derivative of, okay? In lieu, I guess, of putting parentheses in there, that last term dx should stop. It's kind of a way to tell us where we stop at. So we're going to start out by applying that power rule just like we did a minute ago. We now have a formal rule. These are the rules that you need to memorize. The power rule for indefinite integrals. So this is the pattern that we find. If we take the integral of x to the p with respect to dx, then we take that base x, add 1 to the exponent and put it over p plus 1, and then add in your constant because we are doing an indefinite integral here. So let's practice a couple in that vein. So the first thing I would suggest that you do is take your original integral, the integral of 1 over x cubed dx, and let's rewrite it still with our symbol, but write it as x to the negative 3 dx, because we want to put it in its rational form so we can apply the power rule. Then we apply the power rule, which is what we're talking about when we say integrate it, so that we become x to the negative 3 plus 1, which would be what? Negative 3 plus 1 is negative 2 over negative 2 plus c. And the simplification would just maybe be rewriting it back in its fractional form. So I would have negative 1 over 2x squared plus c. So let's try the next one. We want to know what is the integral of the square root of x. So I'm going to rewrite this as x to the positive 1/2 dx. So when I apply the power rule, I have x to the, what's 1/2 plus 1? 3/2 over 3/2 plus c. Simplifying that, that becomes 2/3 x to the 3/2 plus c. If I divide by 3/2, I multiply by 2/3. Okay.
So is the integral just? I'm not sure.
They're pretty much synonymous. Yes, but when I ask you to find the antiderivative, or when you're asked to find the antiderivative, especially at the front part here, they're really asking you to find the capital F of x plus c. Okay. And that's how you find that's how you're finding the integral of indefinite. That's how you find the indefinite integrals. Okay, let's look at this next one. And I'm going to foreshadow this just a little bit. Let me bring it down here for 1 second if I can. I have another rule that we're going to apply actually up there. We're going to apply the constant multiple rule for integrals. It's always a good idea. Take the c out in front. You can move the constant to the left side of the integral symbol, perform the operation on the term on the right side of the symbol, and then stick them back together. That's what we're going to look at here. And that helps out when we do direct substitution and in a U substitution a little later on. So if I apply that principle here, I would have 2 times the integral of sine x dx What is the integral of sine x? What's the undoing of that?
Negative cosine.
Negative cosine x, that's right. So I would have 2 times negative cosine x plus c, or in other words, negative 2 cosine x plus c. Here's another one that is a little bit probably in the wrong section, but we're going to look at it again. We'll practice some more of it a little later. If we apply the constant multiple rule, this would look like 3 times the integral of 1 over x dx. What do you initially want to do? Because that's all we've done so far. Apply the power rule, right? That's what we want to do right here. We want to add, something to this exponent. This, you can't do that. You don't do that because can you think of a derivative? Can you think of a function that when I take the derivative, I get 1 over x, ln x. Okay, so when you have 1 over x to the first power, when I just have this right here, the integral of 1 over x dx, that's actually the natural log surrounded with absolute value symbols plus c. Okay, we'll practice that a little bit more in a few minutes. Now, the next rule that you see down there is talking about below the constant multiple rule, has to do with the same idea that we can do in derivatives, where I can separate these into their individual integrals and take then write them back together as a sum. This one isn't part of that, but what does this look like? If I wanted to take the integral of dx, that's the same thing as saying the integral of 1 dx, correct? All right. Which is the same thing as taking, what's the integral of 1? X. That's right. So this should be x plus c. That's a little bit more like the constant multiple rule, if you will. Let's look at this next one, the integral of x plus 2 dx. I happen to have this surrounded by parentheses, but if I didn't have it surrounded by parentheses, as soon as I got to this dx, I would know that I'm taking the integral of anything to the left of the dx, all right? So in this particular case, what we're saying here is that I can, if we apply that sum rule above, I'm going to say the integral of x dx plus the integral of 2 dx and the integral of x is what? 1/2 x squared plus what's the integral of 2x, and then don't forget your c. Okay.
Do you need that?
Did you have to put a c on the first one?
Yeah.
No, but it's a good question. I have some people who've asked that before. We have a, why do you say no?
This is the same thing.
Still a constant, isn't it? Constant for the first one plus a constant for the second one is still going to end up being a constant. Very good. Okay, y'all do the next one. The integral of 3x to the 4th minus 5x squared plus x dx. So you should have gotten 3/5 x to the 5th minus 5/3 x cubed plus 1/2 x squared plus c. Okay? So just kind of putting it all back together. Yes, ma'am?
Use the constant multiple, but I used the power rule with that.
I used both of them actually. The constant multiple rule, all it's saying is pull the constant off, use the power rule and stick the thing back on. From here, if you had this as, what would that be? That would be 1/5 x to the 5th, right? If you just did all of that in your head, that's the same thing. Sometimes it's a little more helpful to see it when we're doing integration where we have multiple variables. So we might pull it out in front because we're treating that variable as a constant. It doesn't matter. That's an application of it though. All right, let's look at this problem here. I want to take the integral of x plus 1 over the square root of x dx. Now, we have no quotient rule. We don't have a product rule either right now in integration. So instead, we have to apply some different algebra to this particular problem that we have here. Okay. First thing that we're going to do is we're going to rewrite this. So there's a single value in the base, right? In the denominator, there's a single variable. So I could rewrite this as x over the square root of x dx plus the integral of 1 over the square root of x dx. And then change that from its radical into its rational form. And that's going to give me x times x to the 1/2 dx plus x to the, and that was a negative 1/2, I should say, times the integral of x to the negative 1/2 dx. Rules of exponents on that first term there is telling me that I'm going to add those exponents. I haven't taken the integral yet at all. I'm just simplifying this. So I'm looking now at the integral of x to the positive 1/2 dx plus the integral of x to the negative 1/2 dx. Now I can take the integral of it. So here, 1/2 plus 1 would be 3/2 over 3/2 plus 1/2. No, negative 1/2 plus 1 would be positive 1/2, right? So that would be x to the positive 1/2 over 1/2 plus c. Simplifying this, I have 2/3 x to the 3/2 plus 2x to the 1/2 plus c. But those bases are the same. I should be able to, I can leave it there. I'm just gonna leave it like that for now. So you can't apply the quotient rule like we did in the derivatives, okay? You have to apply algebra to simplify it and then take the integral of it. Let's look at this one right here. The integral of sine x over cosine squared x dx. So we're going to use our trig identities to rewrite this as the integral of sine x over cosine x times 1 over cosine x dx. What is sine over cosine? Okay, so this would be the integral of tan x times, what's 1 over cosine dx. So what function, when I take the derivative of it, do I get tan x secant x? Secant x plus c. So we had to rewrite this to be able to then take the integral of it. All right. Let's look at a couple down here. Let's look at the second one. The integral of t squared plus 1 quantity squared dt. So we can't use the chain rule here either. We have to actually expand this, right? Square the first, double the product, square the last. The integral of t squared squared would be t to the 4th plus double the product would be 2t squared plus 1 dt. So t to the 4th plus 2t squared plus 1 dt. Now, if we integrate each of those components, we end up with 1/5 t to the 5th plus 2/3 t cubed plus t plus c. And I don't really have to simplify it any further. Okay, let's look at the last one, the cubed root of x times x minus 4 dx. So we don't have the product rule either. So we just have to expand this. So looking at the last one here, I'm going to rewrite this as the integral of x to the positive 1/3 times x minus 4 dx. And then I'm going to distribute. So that's the integral of x to the 4/3 minus 4x to the 1/3 dx. Now let's take the derivative, now let's take the integral. So this is going to be 4/3 plus 1 is what? 7/3. So this is x to the 7/3 over 7/3 minus 4 to the, what's 1/3 plus 1?
4/3.
So x to the 4/3 over 4/3 plus c, or 3/7 x to the 7/3 minus 1/3, or excuse me, minus 3 x to the 4/3 plus c. Okay. Let's back up. I'm going to do the next one too. I have some other ones I want y'all to practice with. Let's look at this one above it. So I have the integral of x cubed plus 3 over x squared. Having seen what we've already done already, what do you suppose we would do here? Okay. So I could rewrite it, I guess, as the integral of x cubed over x squared dx plus the integral of 3 over x squared dx. Now what? Okay, can I do anything to the first term as well? Simplify it so I could get the integral of x dx plus 3 times the integral of x to the negative 2 dx. Right? Okay. So what's the integral of x? So that would be 1/2 x squared plus 3 times negative 2 plus 1 would be -1 over -1. So negative x to the -1 plus c. 1/2 x squared minus 3 x to the -1 plus c, or 3 over x plus c. You getting the hang of it? Yes? All right. Let's look at 2 more problems we have here. For this one, I want to know what that C value is, right? We keep adding C to this. I want to know what that C value is for a given condition. So I have the function x squared. Oh, that should not right. It should be x to the 5th. I have the function x to the 5th minus 2x squared plus 1. And I have the given condition that the antiderivative at 0 is equal to 1. Okay? So what are we looking at here? Well, remember that the antiderivative is equal to the integral of f of x, right? So the integral is x to the 5th minus 2x squared plus 1 dx. That's equal to 1/6 x to the 6th minus 2 plus 1 is 3, so 2/3 x to the 3rd plus x plus c. But we are saying that for x at 0 on the antiderivative, that function's equal to 1. So we would have 1/6 times 0 minus 2/3 times 0 plus 0 plus c is equal to 1. So c has to be 1 in that case. So the function specifically for these conditions that we found is 1/6 x to the 6th minus 2/3 x cubed plus x plus 1. Remember how we said when we take the derivative, that constant goes away? Well, in this particular case, we want to put it back in for a particular function. All right, last problem. A ball is thrown upward with an initial velocity of 64 feet per second and an initial height of 80 feet. We want to find the position function, giving the height s as a function of time, and when does the ball hit the ground. So a couple of things. Remember how our position and velocity and acceleration functions were all related, right? So if we have the position function, which we typically call s sub t, then the derivative is the velocity, right? And then the second derivative is also equal to acceleration. with the respect to t. So the first thing that we want to know is the ball is thrown upward at an initial velocity of 64 feet per second. And I'm asked to find the position function as a function of time. In other words, I want to figure out what the position function is. That's what I'm looking for in this first question. I want to find S sub t. What I know is from this portion right here, I know that the velocity, S prime, initial velocity, is equal to 64. And I also know the initial height is 80. So I would know S of 0 is equal to, or S of 0 is equal to 80. So I have my position and I have velocity. So if we're looking at this, and I'm trying to go backwards here, first of all, I know that all I have is this velocity part right here. So we're going to use what we know about acceleration and velocity. So we said that the velocity function is equal to the integral of acceleration. Does anybody know? Can somebody tell me what is the constant due to acceleration? Isaiah, you told me this the other day. What's the constant due to acceleration? Not meters per, what's feet? It's feet. What is it? 32
Oh,
feet per second squared. Y'all remember that?
yeah.
Gravity. Gravity is 32 feet per second squared, and it's 9.6 meters per second squared, right? 9 point something. Okay.
21.
Okay. So we're going to use the fact that acceleration due to gravity is a constant. Feet squared, I don't know what it is. I don't know what the units are all of a sudden on it. But anyway, I think it's feet per second squared. That's acceleration. So we can take that fact and we can say, okay, what is the integral then of negative 32 dt? What would that be? What's the integral of negative 32 dt? It's the integral of negative 32. Negative 32t, right? Negative 32t plus c. And I'm going to call this constant 1. Now, that's what velocity is with respect to time. But I know that the initial velocity was negative 32 times 0 plus c1 when it was 64 feet per second. So this C1 has to be equal to 64 because the 32 just goes away. That's the first step, finding this velocity function. Now we're going to come back in and we do the same kind of process using what we know about our position function. So the position function is equal to the integral of the velocity dt. So that's the integral then of negative 32t plus 64 dt. What's the integral of negative 32t plus 64? What's the integral of negative 32t?
Negative 16t.
Okay, so it would be negative 32t squared over 2. I'm just going to write that for now. And what's the integral of 64? 64t plus c, I'll call it c2. So this was, yes, negative 16t squared plus 64t plus c2. But we know from above that this is the initial position was 64 times 0 plus 2 is equal to 80. So C2 is equal to 80. Therefore, my position function becomes S of t is equal to negative 16t squared plus 64t plus 80. That's our position function. So we just had to go backwards, didn't we? You had to take what you're going to assume gravity is either negative 32 feet per second squared or whatever y'all said, the 9 point something or other, which I believe is given in most of the problems, if it's meters. And you have to start with acceleration and work your way back through velocity and then back to position to find out what it is for that particular example. Okay. Now the next question says, when does the ball hit the ground? At what time? So what is the time when the ball hits the ground? What's the height when the ball hits the ground?
0.
Right, so height would be equal to 0. So we could take our function, our position function, negative 16t squared plus 64t plus 80, set that equal to 0 and solve. I'm going to factor a negative 16 out of all three terms. T squared minus 4t minus 5 is equal to 0. So t minus 5 plus 1. T has to be 5 and negative 1. So when does the ball hit the ground? 5 seconds after it's thrown. Okay. So you have a couple of those application problems on your homework. This is a pretty long homework. I think I have about 29 problems on there for you, okay? Because it needs to be, you need practice, okay? So I have 8 problems here. Working on our integrals. Remember, if I ask you to find the antiderivative, it's the same thing without the symbol, only we're finding capital F, right? The antiderivative is capital F of x. If I ask you to evaluate the indefinite integral here, it's the same process, only now we have this symbol. As soon as you get these finished, you're free to go. And we're only working on this for 20 minutes. Here's 3 and 4. You can see the answers that are given there. That should be what, 1/2 z to the 4th. I somehow got rid of that. I think you got moved. We also have 5, 6, 7, and 8 right here as well. Recognize on 6 and 7 that you had not only 1/x, which is the natural log, but you also had on 7 the inverse sign. Okay, inverse sign, so you need to know those. And then on question 8, you just had to simplify that so that you, using our trig identities. Okay, real quick, back to, okay, hold on a second. There you go, go for it. Okay, Nicholas, you got it? Okay, when you're doing Newton's method, I would encourage you to, set up some sort of, I would program it personally into something. Whether that's Excel, I don't know if it was working, I saw you, it looked like maybe it was working in your calculator, I don't know, I hadn't given it that much thought, but it was pretty easy to do in Desmos as well. I just had to label the derivative as something different. Okay, and then I set it up as a calculator. Y'all have a great Thanksgiving, and we'll see you back here on Monday. Don't forget, you have homework too. Okay?